Perfect.
And then I'll turn off my video. You don't have to have, I mean, if you want to have your video on, that's totally fine. You don't have to. And if you have a question, you can just feel free to just start talking. That's fine. Or you can put it in the chat thing. I'll try to like keep an eye on that too. Yeah. So, all right. Now let me figure out how to. Oh, there we go. Okay. I want everyone's. Okay. Now, yeah, okay, so before we start, actually, where's my, sorry, this is gonna be a little, saved offline error, let's not, oh, full screen. There we go. Good, okay. So, yeah, so let me just start with some more introduction stuff. My name's Keegan Stoner, as you've seen. That's my real name, I promise. If you want to email me, this is my email. There's other ones. There's another one that's like k.stoner@northeastern. That one works too. I just tell people this because, you know, this is the one I use for like most of my school stuff anyway. So if you want to email me, that's my email. Again, like I said, I don't know what the state of Blackboard is yet, but it'll be, I mean, it'll be on there soon anyway. And some other resources that you should definitely look at. So like if I'm going through this, if you have a question, obviously feel free to ask me, but if you think like, wow, I don't think I actually know this as well as it sounds like maybe I should, that's totally fine. That's, you know, it's, don't freak out about anything, you know, even if, I know some of these things maybe you learned before and it's just been a long time or something, or you never got a good teacher in the first place or something. So you're maybe a little unfamiliar. Definitely if you think you really do need a full refresher on a specific thing beyond what I'm gonna give here, these two websites are really good. The Khan Academy, I think, as probably people know about, that's really good. I would just Google Khan Academy and then whatever you want, as opposed to like going on their website and searching, because their website sometimes is a little, they want you to like sign up for all these accounts and stuff. Anyway, but if you just Google Khan Academy for like some kind of calculus problem, you can see the full course and they have videos and, you know, all that stuff. And there's plenty of example problems too. That's the big thing. And the other one is, the website's sort of weird, but if you just Google Paul's online math notes, you literally, what you should do is Google Paul's online math notes and then the word that you want. Like you should not go on their website and search because it's awful, but you should just Google Paul's online math notes, integration by parts or whatever, something like that. And if you do that, you'll find a really good webpage. It looks like it's from like the late 90s or something. I don't know why, it doesn't look very good, but it's really good. Like the information is very good. There's plenty of examples, that kind of stuff. So both of these websites are really good if you want an in-depth review of something. But like I said, I wouldn't, you know, you don't need to be like a math expert in all these things. And if you're vaguely familiar with something, but not, you know, you'll see what you need to know in the class, and I'm sure you'll figure out what you need to figure out for the class too. So unless it's completely alien to you, then I would not worry about it too much. Okay, so like I said, I'll go through the. Let me just mute all. No offense, but I'll do that. You can feel free to unmute yourself too, but I'll just do this as a default. So yeah, so the first kind of main concept that's used a lot in physics, especially, it's used in math. You learn about it in math, but you don't really do anything with it. You just sort of learn about it. But in physics, this is used a lot, and it's called a Taylor expansion. And it's just, as you've seen from this in the quiz, it's just if you approximate any function as a polynomial, right? And notice that this is the constant term, this is the x term, there's an x squared term that they want you to find in this, which is they're actually literally asking for. There's an x cubed term, etc. So that's the whole point, is you can approximate any function as a polynomial, and it's only really valid in the range around the point you expand around. That's, you know, that's just how it works, right? So if you want to approximate like a pendulum by some kind of oscillations, pendulums are very difficult because they go up and down as well as going left and right kind of thing. But if you approximate it as very small fluctuations around the lowest point, you can actually just use the first two terms in the Taylor expansion and actually solve it exactly, and it's way, way, way easier. And so that's, sometimes they call it the small angle approximation. So if you've heard that before from physics, the small angle approximation, the I guess that's pretty much it. But that's really just Taylor expansion where you take the first two terms. So for this one, I'll just write the formula. This is one of those like formula things you can't really sort of, you're not going to really read this and figure out. You sort of just have to remember the next term is going to be d2y dx squared. This is just the second derivative. It has a factor of 1/2, and it's evaluated at x naught. I'll explain all this in a second. And it has this squared. Now this is the third term, but let's just write the general term. It's 1 over n factorial. Actually, okay, let me just write this. My handwriting is going to be bad because this tablet isn't very good. Should have just got an iPad. Anyway, oh, sorry, to the end. I think that's right. Actually, I'm just going to Google it real quick because I'm worried I'm off by 1 somewhere. Nope, not Taylor Swift. Taylor series. Yeah, that's correct. Good. Okay. And it's really a sum. So if you want to write the actual whole thing, you'd write it as a sum from n equals 0 to infinity. And then we can write f of x equals this thing. Sorry, I know it's really messy, but so the point is that this is literally Taylor's theorem, what I have in the box. It says that a function f of x is equal to the sum from n equals 0 to infinity, where 0 is this term right here, where I take the nth derivative of f of x. Oops, sorry, again, this should be an n. Evaluated at x naught, which is with the point I'm expanding around. You could also set it to be 0 if you want to. That's a very common choice. And then multiply by x minus x naught to the n. Of course, this is a polynomial with the order of the degree is x to the n, of course, right? And then you divide it by 1 over n factorial because it's just that's like the duplications you get from it. But anyway, really what we're going to use is the fact that approximately it's equal to this thing here, right? Where the dot dot dots we just ignore because we say if x is small, x squared is even smaller, right? That's the sort of thesis of a lot of physics problems. So let's actually apply it in the next question. It says write the first 3 terms of the Taylor series expansion. Now you'll notice that this is cosine x. You'll notice that when you do Taylor expansions, especially for trig functions, sometimes it's 0. Sorry, I'm just seeing if you can see my cursor. You can't unless I draw on it. Okay, good to know. Whoops. So now this is actually a little ambiguous. Some people actually did it one way and some people did it the other way. When they say the first 3 terms, I didn't look. You didn't need to write the first 3 non-zero terms. You could have just written the first 3 terms, even if some of them are 0. Some people did write the first 3 non-zero terms, which are like to order. It's like 1, 3, and 5 or something. If you do that, that's totally fine. But let's just actually plug in this Taylor's theorem. So let's actually use this form here because this is maybe what you'll see if you look something up and then you'll be like, I don't know how to read this. So let's use it. So the first term is 1 over what's 0 factorial? Well, you'd think it would be probably 0, right? Because that's like 0. But actually, what it means really is the factorial is the product of all the numbers, all the integers less than that from 1 to that number n. But if you have 0 integers, then the empty product of nothing has to be 1, right? Because 1 is the thing you can multiply by anything to not change it. So that's a really quick explanation, but there's a whole intuition behind why this is the case. But the point is it's just a 1. And then we have f. Now we have the 0th derivative, really. But what's the 0th derivative? It's just no derivative. So it's just going to be x. And then we evaluate it at x naught. So this is, I'm sorry, I didn't mean to write, oops. I meant to write the actual function. And the function itself is, of course, cosine x. And if we evaluate it at x naught, which is pi over 2, we get cosine of pi over 2. All right, yeah, and this is n here. This n is 0 now for this term. So this, oops. So this doesn't even exist. This thing goes to 0. Okay, so now actually, before we go any further, we can just see what's cosine of pi over 2. It's actually just 0, right? Is that right? Yeah, okay, good. Yeah, it's 0. So this actually is 0. So that's interesting that it has no piece here. Okay, so now let's go to the first term. We have 1 over 1 factorial now. What 1 factorial is clearly just 1. We have d, the derivative of f of dx, the first derivative. So that's just the first derivative of cosine, which is what? Minus sine, right? And if, again, we're going to evaluate it at pi over 2, because that's the point, the x naught. And then we're going to multiply it by, well, now it's x minus pi over 2 to the 1, right? Because that's the, now this term does actually contribute this last term. Okay, now this is not, well, okay, what's sine of pi over 2? Well, that's 1, right? It's not 0. Be very careful. I'm very eager to call things 0 sometimes. This is going to, therefore, minus 1 times x minus pi over 2. Okay, so we have 0 plus this, plus, and now, what about the, it's really the third term, but it's n equals 2, right? Because we started with 0. You have to make sure that you start with 0 here. Okay, so the third term is, now it's going to be second derivative. So it's going to be 1 over 2 factorial, which is 2 times 1, which is just 2, times the second derivative of this. What's the second derivative of cosine? It's just minus cosine, right? Because we take one derivative, we get minus sine. We take another one, we get the minus comes out, and we get cosine of pi over 2. And we really, of course, get this too, but we know that we don't actually need it for anything because we have, again, cosine of pi over 2 like we had before, which is 0. So this one is literally just minus x plus pi over 2, right? This is the first 3 terms, and of course, there's only 1 term. But it is the first 3 because the other ones are actually 0 of this function. Now let's actually, okay, that's fine. That's the answer. That you could look that up, whatever. What's the actual, like, how do you think about this? Well, notice that notice here, this tells you, this is a polynomial with a degree n, okay? If the degree n is even, then you'll have what's called an even function, right? An even function, I'll write this in. Can I move this over? Kind of. Okay, I'll write this over here, and it's kind of annoying. Actually, well, okay, that's fine. A function that's even has this property, right? This is even. And a function that's odd has this property. Yeah. Okay, in other words, even functions are sort of symmetric, right? This is sort of symmetric, and odd functions are sort of anti-symmetric. And a sort of hint is that all the terms in the Taylor expansion have to match whether if the function is even or odd, they have to also be even or odd. And a polynomial with degree n, if n is even, it's an even function. If n is odd, it's an odd function. You can imagine that, like, this is x squared, y equals x squared. This is an even function because it's f of minus x is the same as f of x, right? And y equals x, which is really x to the first, of course, is odd because y of minus x is the negative of y of x, right? Does that make sense? So the point is that, and this is a special case. Not every function is like this. Like, there's plenty of functions you could draw that just aren't even. Oops, sorry, this is an x, not a lambda. There's plenty of functions you can draw that are not even or odd. So this isn't always true, but in this case, cosine, what kind of function is cosine? Cosine is actually an even function, right? Well, okay, sorry, this gets a little confusing. Cosine around the point pi over 2 is actually odd around that point because cosine looks like this, right? This is cosine of x. And this is actually even. It's not really centered, but it's supposed to be even. It's supposed to be symmetric, right? But because we're talking about the expansion around the point pi over 2, right? Around this point, it's actually odd because if we go this way, we have to go down, and if we go this way, we have to go up. So it's actually odd around this point. So the Taylor expansion for this is going to be only odd functions like this x, right? X is x to the first, which is an odd function. I know it's a little confusing because I was just saying it's even or odd. But if you expand x around 0, if you expand any of these Taylor expansions around 0, they will always match just the function itself. So the Taylor expansion for, actually, I'll write it over here. I know, I'm sorry, I'm jumping around a lot, but the Taylor expansion for sine x is x minus 1 over 3 factorial x cubed plus dot dot dot. And the Taylor expansion for cosine x is 1 minus, this is at x, x naught equals 0. And cosine x is 1 minus 1/2 x squared plus dot dot dot. Okay, so these, if you go expand around x naught equals 0, which is like, I'm going to say 100% of the time in physics, you expand around x naught equals 0. There's almost no reason you do any other point except for this stupid problem in this quiz. But the Taylor expansion around x equals 0 matches, so sine is an odd function. And so all of the powers that appear are odd. The other ones will always be 0, right? If you plug in, for example, the first term that would go here, if you plug it, that would go here. If you plug in sine of 0, you get 0. And so this term doesn't even exist. Whereas cosine of 0 is 1. That's where this 1 comes from. Anyway, so that's kind of interesting. You'll also notice that, as we'll see later in this little quiz, that e to the x actually can be written as cosine x plus sine of x. Well, let's just say it like this for now. This literally was one of the questions in the quiz. And you can actually see that this is true. Sorry, it's a little messy looking. So e to the I x equals cosine x plus I sine x, which is supposed to say. And we'll see that this is true. Well, I won't show it, but if you look it up, you'll see it's true by Taylor expansion. The Taylor expansions of both sides, if you add these together with an I, then you'll see that the Taylor expansions add up. Meaning that the sum of the right-hand side's Taylor expansions is equal to the left-hand side's. Okay. So, right. Now let's go, let's move on. We're done with Taylor expansions. I don't want to overstate their importance. They're very important, but you don't have to do them a lot. You'll sort of do one for cosine like 4 times, and that's it. You don't have to usually do them for arbitrary functions, but that's the formula you know to do. It's just derivatives. Okay, so this one is called a binomial expansion. It's sort of a different type of expansion, and it has to do with functions that are written like 1 plus epsilon to the n. Now, because there's an n here, we can write this. Actually, let me start with something a little more. Oops, sorry. This question seems really out of place, so I want to sort of qualify it. This, oops. Okay. This x plus y to the n. What is x plus y to the n? It's obviously, if you don't know what n is, you can't really write it. But we know that it's something like, it starts like x to the n plus what's going to be next? Well, it's going to be something with x to the n minus 1 times y to the first, right? Plus dot dot dot. And then the last term is going to be y to the n. In other words, the n powers are going to sort of distribute themselves so that they sort of sum up to be n. Like, notice that in this term here, it's when you have a product of n of these where you selected one of the y's and the rest of them were x's. The n minus 1 were x's. That's where this term comes from. And dot dot dot, and that's how you do it. If you could write it with 3, you could write it out with like a low number if you want, but I'm just trying to do it in general. And what we see is that, well, how many terms are going to have this form here? How many terms are going to have n minus 1 x's and 1 y? Well, clearly, if you wrote this out, if you wrote out the left side, there'd be n terms like that, right? Because there's literally n terms that you can choose the y from. So this number here is actually going to be n. And then, so the formula for given a random term in this, the formula for what the coefficient is called the binomial coefficient. So this is called the binomial coefficient. And it's basically like, if the power of x is k and the total power is n, what's the coefficient for that term? And it's called n choose k, and it's it's a whole thing in probability that's used a lot. Well, I'm not going to go into it because we don't need it for anything. But for this term, or for this question, all that you need to know about is this thing here. They're saying that, well, okay, there's two things. So let me. So the point is that 1 minus epsilon, 1 over 1 minus epsilon is the same as 1 minus epsilon to the minus n, right? Now, this is 1 minus epsilon, which is just like x plus y, right? Where y is minus epsilon and 1 is x. And because they say specifically epsilon is very small compared to 1, it's much, much less than 1, that means that this term here, which has 1 y in it, which is really going to become 1 epsilon, is okay, because that's an epsilon. But the next term has a y squared in it, and every other term has higher powers of y in them. Those are going to be really small. So when they say it's small, they mean to first order. So I'll write that. To first order in epsilon. That's what small, oops, well, I meant to say that's what the word small means here. Small means to first order an epsilon, meaning that epsilon squared, it can just be 0. Meaning that this term, which is just in our, now this is x plus y, but in our version it's 1 and epsilon. This term is going to be there. This term is going to be there because there's only 1 epsilon right here. But every other term is going to be 0 because they're going to be small. So the point is that we just pretend it's just these two terms. The first one is clearly going to be 1 because it's 1 to the n, and this, yeah, so it's going to be, here we go, 1. And the next one's going to be, well, it's going to be n, which is the power. In this case, it's going to be minus n, times y, and y we already said is minus epsilon, times 1, this x here is going to be 1 to the n minus 1, which is just 1, of course. So this becomes 1 plus epsilon, so that's it. Right, so the main point of this question is, it's a little confusing because you have to just know that it extends to the negative numbers here, these negative numbers, the negative powers. That's just a property of, you can find, that's actually true in Taylor expansions too, and all these other things. So it's a little, that's like not very intuitive, I think. But the point of this question, I think, was just to get you to realize that if you write x plus y to the n, you can expand it in powers of x and y, such that each coefficient is some known thing. But the first one's actually easy to find just by hand, because if you just eyeball it, you can kind of see that there should be n copies of this term. Anyway, that's called the binomial coefficient. So, like I said, they're used a lot in probability. I don't think we'll use them very much, but we don't really ever use the binomial expansion for things in this class.
Sorry, can you repeat some of that? You said that in this case, x would be 1, and then y would be negative epsilon.
Yes, yeah.
And then it's to the negative n power. So then when you do it out, you said you have x to the n. So that's where you got the 1 to the n.
Yeah.
And then you're doing plus n times x to the n minus 1. So
right.
Where does the negative n come in the second term?
Oh, yeah, so, okay, here, I'll do it like this. Oops. Okay, I hope this isn't more confusing. I'm going to say x plus k, or x plus y to the k, to first order in y is going to be x to the k plus k times, times x to the k minus 1 times y, right? That's all to first order in y, that's it. Then we're going to say x goes to 1, y goes to epsilon, and k goes to minus n, right? Then this formula here looks just like this thing here, which is what the problem gives us. And if we make these 3 substitutions, and if we do that, now the power, which used to be n, is now minus n, but that's fine. We just replace it with minus n, or in this case, I call it k. So k is now minus n.
Okay.
So therefore, oh, I'm sorry. Oh, yeah, no, that's right. Sorry. Yeah. So this becomes 1 to the k, which it doesn't matter what k is. It's just 1. k goes to minus n, and x goes to 1 to the anything is 1, and then y goes to minus, oh, sorry, I'm sorry, minus epsilon. Yeah, and then this is plus n epsilon. Yeah, so we had to make these 3 substitutions because then this y plus, or x plus y to the k matches 1 minus epsilon to the minus n. Does that kind of make sense? I mean, if it is unintuitive why you're allowed to use negative numbers as the powers.
Yeah, I think I understand why you can do the negative as the powers. Is there supposed to be like a y to the k term at the end of this?
Yeah, so this is actually, so if I write, let's do x plus y cubed. So if k is 3, we get x cubed plus 3. I just remember what they are. And I'm using these 3's are actually, I mean, you can do it out and you can find it's 3, but it's actually called the binomial coefficient. Now, this is fine. This is actually literally what it's equal to. But if if I know that y is going to be epsilon or minus epsilon or whatever, and if epsilon is small, so over here when I wrote,
I understand now. Okay.
Yeah, epsilon squared, which is this term
is
and
0.
this term, is 0. So this is literally 0, 0. Now, of course, for any, just because I picked 3, any higher power than that, that's fine. But this is always going to be whatever the power is. N,
it'll just stop there.
Or k, and it'll always stop there because every other term will have y to the squared and above.
Okay.
Yeah, so the key point here was that, yeah, this would be impossible to do if they didn't tell you it's small because we don't know what n is, right? You can't just write all the, So the fact that epsilon is small means that we know this term is the only one that's going to matter.
Okay.
All right. Yeah, so that was probably the most common answer on the quiz that people seem not to have any idea how to do, which is very understandable.
Can you review the binomial coefficient?
Sure. Oh, I'm sorry. I muted it. Sorry, you can unmute yourself. I didn't mean to mute you when you were talking. Yeah, you want me to go over the binomial coefficients? Yeah, so what they are is that the power, so if you have x plus y to the k, this is x to the k, dot, 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 dot. We know we can write these other terms. And at some point, oh, actually, sorry. Well, okay, that's fine. Okay, and at some point, we have a term that looks like a number times x to the, I'll call it, I'll call it L. X to the L times y to the, and it has to be k minus L, right? Because the total number of powers in each term has to be k, right? Because it's just combinations of x and y, right? So if this is x to the L, this must be y to k minus L. And this number of powers, this number here, basically it's the number of combinations of ways to get this here, is a number called k choose L. You say it like k choose L, and it's actually equal to, I think that's right. It's actually equal to this, which is a bunch of factorials that you divide. Actually, let's just check if this is right. I know for x cubed, it's clearly going to be 3, right? Because if you just do it out, you'll see it's 3. And so therefore, my k is 3. And for this term here, my L is 1. So I'm computing 3 choose 1, which is 3 factorial, which is 6, over, and L is 1, so this is just 1, times 2 factorial, right? Because k minus L is 3 minus 1, which is 2 factorial, which is 2, and this is 3. So yeah, this, so in other words, and I should really put plus dot 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 y to the k as well, because we know if I put this one, I should put the other one too. But anyway, any term in the middle must have a total power of k, but it's split between the x and y's, and what's the coefficient of that term? That's called the binomial coefficient, and you can It's just given by this. There's just a nice little notation called the like K choose L or N choose K or whatever. They use different notations, but yeah. Does that?
It reminds me. Am I completely off base of thinking that as similarities to like some of the questions later where it asks for the combinations or choose? Just the factorials over the divided by another factorial just reminds me of that.
Where it asks for the combinations. I mean,
I remember doing a combination question. Or maybe that was something else I was working on that gave me a combination.
Comment on the GRE.
That's probably where I saw it then.
Yeah, I don't see it up here, but basically any question that asks about combinations, can use this K choose N thing.
Feedback.
Right?
Eric, I think your feedback is.
Yeah, there's a little.
Just mute after you're done speaking, please.
Yeah, just try to. Yeah, so basically any question. Yeah, I don't think it's on here, but I'm sure you're. Basically, anytime you use combinations or permutations, you will use the binomial coefficient. They come up all the time because there's a thing called the binomial distribution, which is not the same as it's not. I mean, it's kind of the same as this, but it's not. You don't literally use it for the same things. The binomial coefficients is literally just a method to find an arbitrary coefficient of this expansion. Binomial distribution is a probability distribution, but that's used all the time in probability and in combinations. And how many ways can you arrange K things in N places or whatever, right? That's exactly the same thing. So yeah, you're absolutely right that it's the same thing. Absolutely right. It's the same thing.
Yeah, that answers my question. Thank you.
Yeah. Yes, you're actually much more likely to see it in those instances because these kind of expansions you can just look up. You don't, but with distributions, you might need to actually arrange things and count things, right? It's it's kind of the same thing because in the sense that this is the number of ways you can arrange K total things and split them between X and Y, right? That's sort of another way to say it. Anyway.
Could you connect the binomial expansion back to something that we might see in like physics, or when would we use this?
Yeah, that's what I was thinking. I don't know. I mean, I really don't know, other than, yeah, I mean, other than the fact that things of this form, this function that has this form, it's 1 plus some small number to the nth power, you can always approximate it by, 1 plus epsilon to the n, you can approximate as 1 plus n epsilon. This fact you might use in like optics or something. This whole distribution stuff, I can't think of, I'll try to think of something. I can't think of any time you would use this in this class to actually use it for like a distribution or whatever.
Okay.
Yeah, I can't think of anything. I mean, yeah, I'll get back to you. Next week I'll come up with a problem if I can think of one that's useful. But yeah, I kind of went, I guess this is a little off the track. Okay, so the next few questions are just derivatives and integrals. So I'll just go over them real quick. I assume that I think a lot of people pretty much got them completely right. If you're really lost with these, that's just you can either let me know on with an email, and I'll give you some specific links, or you can just go to those links at the beginning of this thing. If we have the derivative of e to the something with an x in it, well, we know we're just going to get e to the minus ax squared, which is the function itself. The derivative of e to the any function of x is always the returns e again to the same function times the derivative of the inside. With the inside is just what the function, the exponent is of the derivative. This is going to be minus 2ax, right? So this is just minus 2ax e to the minus ax squared. So that's this derivative. This, by the way, this function here is called a Gaussian. I'm not sure where you'll see it. It's all over the world in nature, but we'll see. We'll talk about it. But it has the form e to the minus something x squared. This one is just integral of dx over x is usually how it's written. You just sort of treat dx like a variable. This is just log of x, natural log of x, plus a constant. The constant, I wasn't too, I mean, if you're in high school, I'm sure it was very important that you added the constant. I'm sure you get points off if you didn't. In physics, you almost never do an indefinite integral anyway. So it doesn't really matter. So I didn't really care. But yeah, it's natural log of x. That's it. Yeah, you could put log base anything here actually, because they only differ by some multiplicative thing, which can be factored out into a constant. But you should just generally talk about natural logs anyway, because they're easier. Okay, this one is a definite integral, which is good. We can see that there's two terms here. The first term, the two terms will because there's no there's nothing multiplying here. It's literally just two terms. It's literally just two separate integrals. The first one is just x, because it's the integral of 1, evaluated at 4 is 0, minus, and now what's the integral of x to the third? Well, it's going to be x to the fourth over 4, right? Evaluated at 4 and 0, and all we do is just find each of these, the top minus the bottom, right? So 4 minus 0 is 4. 4 to the fourth is 64, I believe. No. 4 to the fourth over 4 is 4 to the third, which is 64. Minus 0 is 0. So I think that's right. Yeah, because 16 times 4 is 64. And this therefore is minus 60. So there we go. I'm going a little fast, I know, but just feel free to let me know if you didn't follow something. I'm just going fast because I'm sort of applying rules, and I'm hoping you remember the names of the rules when I say them. But feel free to let me know if you don't, or say something in the chat. This is just integral of cosine. We already sort of did this anyway. It's going to be minus sine, of course. It's just theta here. So it's not like we have to do any chain rule stuff or use substitution or whatever it's called. So this is going to be minus sine of theta, evaluated at 0 to pi over 2. What's sine of pi over 2? That's 1. So it's minus 1. And then sine of 0 is 0. So I think it's just minus 1. Did I do that right? Yeah, okay. Hope I do all these right.
Is the integral of
yeah,
cosine negative sine, or?
Oh, I'm sorry.
I always get those mixed up.
You're absolutely, yes. Thank you very much. This is why, yes. Sorry. What? Yeah, because we did this before we did the derivative. That's why I was confused. Yeah. So sine derivative goes to cosine. Derivative goes to minus sine. And of course, you sort of already know that if the derivative of minus of something, you can just factor out the minus and it becomes minus cosine. And then because we know minus cosine, because cosine goes to minus cosine goes to plus sine, right? So, and integration just goes the other way. So you're absolutely right that integral of cosine should just be sine. So it's plus 1, yeah. Thank you. Good. Okay, so this is another exponential integral. Oh, sorry, we didn't do one here. We did a derivative. Exponential integral is going to be, well, it's going to be the opposite of the derivative, right? So actually, this is a u substitution, right? We want to set u to be whatever's in the exponent. Therefore, du is, well, really, we should say du dx is the derivative of u, which is minus 3. Therefore, we can say du equals minus 3 dx, right? That's sort of moving the dx over. Some people will tell you that you're not supposed to move differentials around. You don't have to listen to those people. That you can totally do that. It's fine. And then this becomes integral from 0 to 1. Well, okay, it's not quite 0 to 1 anymore because this is not an x integral anymore. It's a u integral, but we'll plug it in later. This is going to be e to the u now because u is net minus 3x. And now, well, we have a dx here that we have to substitute, but it's not just du. Clearly, it has to be du over minus 3, right? Because we have to solve for dx here. So over minus 3. Now we can factor out a minus 1/3, and we just get e to the u du. e to the u du integral is literally just e to the u. We have evaluated it from 0 to 1, but again, it's be very careful here because this is not u equals 0 and 1. This is x equals 0 and 1. So we could even write x equals everywhere. Yeah, again, I'm sorry, it's messy. Whoops, that's a 3 over 3. And then we just plug back in. Oh, there we go. Just plug back in 1 and 0, and we get e to the -3, and then e to the 0, of course, is just 1. So we get like that, I think. Now, this is just a number. You can figure out what it is. I don't know what it is, 0.6 or something. No, it's not. It's positive, and it's, let me look it up. I don't know what it is. It's not an interesting number is the point, but that's what it is. Yeah, so again, all we used is use substitution here. And yeah, all that we did, of course, was just take an integral. We know how to do this integral, but we only know how to do it when this variable here is the same as the variable in the exponent. And they're not quite the same. So if we do a u substitution, we can get everything in terms of u. And then just keeping in mind, we have to switch back when we replace the limits of the integral. Okay. All right. Now it's, okay, so here's some log rules. So we know that log of AB is just equal to log of A plus log of B. And I'll just, I mean, this is just a thing where I'll just tell you the rules because you sort of just apply the rules for this question. A over B is log of A minus log of B. And actually, let's just look at this one a little more closely. What if A was equal to B? Then you'd have log of A squared. I'm going to put A to the n. If you had log of A squared, it would be log of A plus log of A, which is 2 log of A. And in general, log of A to the n is n log of A, right? So this actually is a consequence. This is actually a consequence of this first thing here, because you can just say, okay, well, what if you just put a c here too, and then you'll get plus log of c, right? Let me just undo that. It doesn't look as nice now. And if you just put a bunch more letters here, and you set them all equal, you'll get n copies of it, and therefore you'll get n log of A. And what if you'd actually had 1 over A? You can treat that like A to the -1, so n equals -1, and then you get minus log of A. And that's actually gives us this second rule here, because it's really this line here is really just A times B to the -1. So you say it's log of A plus log of B to the -1, but log of B to the -1 by this rule we know is minus log of B. So anyway, I'm not trying to make it more complex. I'm just trying to say that there's actually only sort of one simple rule of logs, which is this one, and everything kind of follows from it. Although it's probably easier to just memorize them. But yeah, so that's the log rules. I'm just trying to think. There's not really any more log rules, because any other complicated function basically doesn't simplify at all with logs. So, I mean, of course, we also have the fact that log of e to the x is just x. And also e to the log of x is x. So the fact that log is the inverse of e. By the way, whenever I write log, it's the same as ln. So because in physics, and I literally, there's like one place in all of physics where you use log base 10. Everywhere else you use log base e. The other place I'm thinking of is like sound design. So I don't know if people work at like Bose or whatever, but I'm sure with like decibels, there's some, I don't really know how decibels work, but something with log base 10, I think. So anyway, everywhere else though, you use log base e. They basically work almost exactly the same though. It's not like a completely different thing. It's just that these are, of course, are only true when you're using log base e. Otherwise, there'd be some factor here. You could also replace this with log base 10 and put a 10 instead of an e. Okay, this one. Okay, now we're actually going to use the rules to solve something. well, solve for x, we have 3 equals e to the blah, blah, blah. We just saw over here that if we just take log of e something, it just brings everything down, brings the exponent down. So we have log of 3 equals log of the right-hand side, which is going to be minus 5x, right? Because log of e to the minus 5x is going to be minus 5x. Log of 3 is literally a number, so that's fine. So we can just literally solve log of minus this over 5 is equal to x. That's it. It's just this thing. Again, you could solve for what this is. It's some number. It's a small number. But you might as well leave like this because this is sort of an exact answer. It's usually better to leave things as exact answers than decimal approximations, unless you're using it for some estimation. Okay. All right, so now 11 and 12. Now we're getting back. we went from number 3, which was sort of really outside the, wow, this is ugly. I'm sorry. This hopefully you can read this later. Yeah, question 3 was like one of the main ones that was like really weird and different from all the other ones, and something that's like I sort of didn't know how to do when I read this the first time. And now we're getting back to things where these are things you're actually going to use, but you're only going to solve them like you're going to solve the same ones over and over again, the same differential equations. But differential equations are definitely something we actually use, and it's something that most people probably don't have a ton of experience with because they're really hard, and you have to take. Usually, they're not taught until some special class. The point is that this differential equation here, forget about the initial conditions for now. This differential equation here has a solution, and you'll see this exact identical differential equation all the time, and it always has the same solution. And I'll tell you what it is. It's just going to be y equals a cosine x plus b sine x, right? Now, a and b are not, they're just numbers. This isn't the final answer yet because we have to solve for a and b. But this is the only solution to this differential equation, okay? This is sort of the whole thing. The reason is because what this is saying is that, what this differential equation is saying is that we have a function y of t whose second derivative is the minus of that function itself, right? What's the only function? We actually just wrote it right here, right? Here, we have functions whose, when we take 2 derivatives, we get the minus of the function itself. Sine does that and cosine does that. Now, you always have to take my word for it that there aren't any other functions that do that. You might think about, oh, what about like e to the ix? If you take 1 derivative, you get I, e to the ix, and then take 2 derivatives, you get minus e to the ix because the next derivative brings another I and it's minus 1. That's true. This also has the same property. 2 derivatives is the minus of the function itself. But of course, we know by Euler's formula, this is actually equivalent to this anyway. So this is sort of the only function that has this property. Let me just write this here so I don't forget to talk about it in a minute. This is like the only other differential equation you'll ever solve, which is this one. In this class, I mean, I don't know, perhaps you'll have other things to do, but in this class, there's basically just these 2 equations. And in some sense, this one is somehow called stable, and this one's sort of called unstable, right? I just sort of made that up, but like that's basically how you should think of it. This one's stable because it's saying that 2 derivatives, which in physics usually means like acceleration, for example, is minus of that function. This is sort of restorative, and this is sort of amplifying. This sort of says that any deviation is the same direction as the function itself. This says that deviations give rise to things in the opposite direction, like back toward the equilibrium. So you should kind of think of this as like being, let me write this in red, stable, and this is unstable, right? And we'll see when we solve the second one that it actually literally is unstable. And this is the reason I say stable is because cosine and sine are bounded, right? They don't blow up to infinity, right? Polynomials and all that stuff blow up to infinity. Sine, cosine do not blow up to infinity. They go between values. So now, okay, let's stop talking. Let's just actually solve it. We have to actually plug this back in because we don't know what a and b are. What's the second derivative of this function? Well, I'll write it as y double prime. Oh, actually, sorry, these should be t's because the variable we're differentiating with respect to is t. So y double prime is, actually, sorry, let's take one, let's just do it I'm going to mess it up if I do it all too fast. Let's do y prime, and that's going to be, well, what's the derivative of a cosine t? That's going to be minus a sine t, and the other one's going to be b plus b cosine t, right? And now if I'll take second derivative, and we get minus a cosine t minus b sine t. And luckily, as we expect, this right here, the second derivative, is actually just literally the negative of this one, which is literally what this equation says. Okay. So now what we have to do is plug in our initial conditions, which are here. At t equals 0, these things happen. That means if we have to plug in t equals 0, well, the first one says that at t equals 0, y equals 5. So we know that here, if we plug in t equals 0, we get what? Well, what's cosine of, we have a cosine of 0, which is 1, so a, plus b sine of 0, which is 0, so that doesn't matter. And then we know this has to be 5. Well, that was easy. We know a equals 5 now, so that's fine. Now let's check the second initial condition, that again, it's at t equals 0, dy dt is 0. Well, that's this one, right? Plug in 0 again, we get the first term goes away because that's sine of 0. The second term gives us b cosine of 0, which is 1. So we just get b. And this must be 0. Oh, this tells us b equals 0. Therefore, we plug back in our initial, we plug back into our initial equation with the solution we just found. Luckily, they didn't contradict themselves. If they did, you probably made an error somewhere. And that's it. And 5 cosine t, of course, as we've shown in the general case, 5 cosine t has the property that two derivatives of it give a negative of the original function, and they have the property that at t equals 0, the function is equal to 5, and at the first derivative at t equals 0, the function is equal to 0, right? And it's the only one, that function, that's like that. So yeah, that's it. Now, the question you're probably asking is, how did I know it was this in the first place? And the answer is, you sort of don't. You just have to like remember it. I mean, you could guess things, of course, but if you try a polynomial, you'll see that it's never really going to work. You just sort of have to remember that. I mean, again, it's like, how do you derive that it's cosine sine? All of differential equations, the class, if you are taking the class, all of differential equations class is just learning good guesses for things and then checking them. That's kind of the whole thing. There's no better way to do it. I'm sorry. I mean, there is a better way. You can go on Wolfram Alpha and ask it because it knows a lot of examples. But if you actually have to do it, you just have to remember that this is the function whose second derivative. Sometimes it's better to say it out loud. Whose second derivative is minus the function itself. The other one you will have to talk about is this sort of. Oh, and sorry, I also just meant it's stable because, again, like I said, cosine of something is just bounded. If you sort of push it a little bit, it sort of will tend to come back to where it started. It goes like this. So imagine a pendulum. Pendulum might oscillate back and forth. So this has to do with oscillations. And we know it's oscillations because it's stable, because this tells us that things tend to want to restore themselves. That's sort of the philosophy, I guess you could say, behind it. Now let's go to this unstable one. Well, what function? Again, you just have to know what function it is. There is one function whose second derivative is equal to the function, so without the minus sign. And that function is e to the x, right? Because if we take two derivatives of e to the x, we just get the function itself. Yeah, with a constant. But also there's actually another one, which is e to the minus x, right? Because if we take one derivative of e to the minus x, we get minus that front, but if we take another one, we get the plus again. So both of these functions have this property, and therefore we need to add them in a linear combination. This is actually true for this first one too, because cosine and sine both satisfy this property separately. We have to introduce these a and b coefficients. So the same thing for over here. Because e to the x and e to the minus x separately solve this property, we have to include these coefficients here. Then we would plug in our initial conditions. We definitely need two initial conditions for both of these differential equations, and the reason is because there's two derivatives here, but also because there's two, we know there's a and a b here. So we must have two conditions that tell us. Usually they'll just tell you the function and the derivative at time 0. That's a very common one. All right, maybe they'll tell you a different time, but it'll usually be pretty easy to solve. But yeah, and sorry, I should say, so the reason it's unstable is because e to the x, if you plot it, goes like this. It goes to infinity, right? And so you can imagine, what if you have like a pendulum that if you push it slightly, it wanted to respond by pushing itself to infinity. Well, that's obviously not really how pendulums work, but well, you can imagine a pendulum stood on its, like you take a pendulum that goes all the way around and you point it directly upwards. That's called an unstable equilibrium, because if you push it in, let's say, to the right, it'll respond with a force, which is sort of like this. So we'll go through this, but this is like an acceleration. So it's sort of like a force. It'll respond with gravity will respond with a force going in the same direction you pushed it. So that's why it's unstable. And it will go, obviously, it doesn't go to infinity, but it goes away from where you pushed it. On the other hand, if you have a pendulum that's at the bottom, like an actual pendulum that's sitting at the bottom of the where it swings, if you push it to the right, it pushes back to the left and it wants to come back. Therefore, it's stable and it oscillates. So those are basically the two initial equations. Again, the reason I say those are the only differential equations you'll use is because, I want to clean it up just a little bit. The reason I say it's the only differential equations you'll use is because in physics, we pretty much only use things where the force, which is the left-hand side of the second derivative, left-hand side of these differential equations, is proportional to, the force on the right-hand side is proportional to a distance or function itself. And on the left-hand side, we have the actual expression for the force from Newton's law, Newton's second law. So anyway, the point is that you only see a few of these. We'll actually do, in the spring, we're going to do ones where we add another term, which is a linear, like this type of term, where we add a linear component of like a first derivative to this equation. All that does, we'll see. I'm not going to solve it now because it'll be like, you'll see. It's actually not that hard. All this is just a drag force. And we'll talk about that in the spring. I'll go over this, basically all of this again when you need to solve these. Okay, does anyone have any questions about these two differential equations? All right. Yeah, again, I won't go through, I don't want to have everyone learn all the methods of differential equation solving and then use one of them in the class. So during the class, I'll spend time in my office hours going over any new differential equations techniques we'll need. Okay, so the next one is changes of variables, but it's specifically changes of variables with differentials, which is a little trickier, right? It's not just substituting things. And so what we have to do is we'll say, well, we have this expression here, integral of, let me go back to black, integral of omega squared d omega. They tell us what omega is in terms of lambda, and they want to write it as an integral over lambda. Now, what you might think, why are we using these crazy Greek letters? This has to do with a light intensity, and this is the omega, the frequency of light, and lambda is the wavelength of light, and this is the relation between the frequency and wavelength of light. You can see because the c on the top is the speed of light, and 2 pi is because omega is an angular quantity. Anyway, we'll get to all that in the future. You don't have to remember any of that. That's just the context of this question, why it looks so crazy. We will actually do integrals like this. I think there's a homework problem that's literally basically just like this. And the point is that, well, we know that omega squared, let's just write omega squared d omega. We know that omega squared is just 2 pi c over lambda all squared, right? Sorry, it's so messy. Actually, let me use the bigger, there we go. There, it's a little bigger, okay. Omega squared is just 2 pi c over lambda all squared, right? Because that's just lambda squared. Now, what's d omega? Well, cross this out. D omega, well, we know what omega as a function of lambda is, so therefore we can compute d omega d lambda, right? This is just the derivative of the omega function as a function of lambda, which is just 2 pi c which is a constant, right? All these are constants, times, and then we get -1 over lambda squared. You can figure this out because it's just lambda to the -1. And then if we use the power rule, we bring the -1 down and it goes to -2. And so we get this. Therefore, d omega by itself is -2 pi c over lambda squared times d lambda, right? All I did was move the d lambda to the right side again. So now we have a relation between the differentials of omega and lambda. And now all we have to do is put it together. We have omega squared, comma, omega squared d omega is equal to, okay, so it's 2 pi c cubed, I guess, right? Because we have 1 from the d omega and 2 from the other, from the omega squared, minus from the minus and the minus from this minus. Then we have lambda to the third. Is that right? Yeah, I think that's, oh, sorry, to the fourth. To the fourth, d lambda, right? Sorry, I'll erase that. Okay. I think that's right. Now, of course, we could actually integrate it, but they don't ask us to do that. Yeah, I think that's good, right? Yeah. Yeah, all right. So that's what they wanted us to do, is just to find this thing. Now, I guess the weird thing is that it seems like weird that there's a fourth power of lambda in the denominator, but that's just, again, from the fact that d omega is not just d lambda. You can't just substitute one for the other. There's some factor associated with the derivative of omega as a function of lambda like this. So this is a common technique, as you've seen, to take derivatives of things which are written as fractions of differentials and then just move the denominator over to the other side so we get this. Yeah. All right. Okay, next question is completely different. It's about a matrix product. So what we do is we take the so this is, first of all, let's talk about the dimensions. This thing is a 3 by 3 matrix. The first 3 means the number of rows, and the second 3 means the number of columns. So there's 3 rows and 3 columns. This second object is, it is a matrix. It's a 3 by 1 matrix, but you can also call it a vector, right, with 3 components, right? That's usually what they typically call it if it only has one. If it's a column vector, or sorry, a column matrix with 1 column, they usually call it a vector. And so you can only multiply objects in linear algebra. You can only multiply objects in here, matrices by matrices or matrices by vectors, etc. You can only do that if this number and this number, the inner numbers, match. Otherwise, it's literally impossible. It doesn't make any sense. In this case, they do match, and the output is going to be and you just take the other numbers, so it's 3 and 1. The output is going to be a 3 by 1 matrix, which is literally just the same as this. So what this is going to do is just rotate, or transform, I should say, this vector. It's going to take this matrix, is what it's going to do is take this vector and transform it so it's a different vector. So in this case, matrices are usually sometimes called linear transformations. Not sometimes, they're always called linear transformations, because what they do is take vectors to other vectors. So it's just like taking the plane, or in this case, the 3D space, because it's 3 dimensions, and sort of doing some transformation. Maybe it's stretching it and rotating it and stuff like that, and giving you all the vectors. The input vectors are going to different output vectors. Now, that's fine. That's all philosophy and stuff. Let's actually do it. What you do is just take the dot product, if you want to think of it that way, or you just take this first row here and dot it with this column. Dotting it means, of course, you just take each component times each component and add the total things together. So you get 2 times 2 is, this is, by the way, the first entry. 2 times 2 is 4, plus 0 times 0 is 0, plus 1 times 1 is 1, right? The second one, let me erase this now. The second entry, which is the middle entry of the output, is, well, we have 0 times 2 is 0, 4 times 0 is 0, 2 times 1 is 2. So we had 0 plus 0 plus 2, right? And then for the final entry, the bottom entry, we have 1 times 2 is 1 times 2 is 2, plus 0 times 0 is 0, plus 1 times 1 is 1, right? Oh, sorry, I forgot. I keep forgetting you can't see what my I have my cursor here. Can you? No, it looks like you can't. Sorry. Yeah, so what I'm doing is doing this times this, plus this times this, plus this times this, right? So I know it's really messy, but anyway, that's this first entry here. And then if we simplify everything, we get 5, 2, 3, right? So what this did is that this matrix took a vector 201 and transformed it into a vector 5, 2, 3. And it does that to every vector. Of course, every vector gets transformed somehow, and therefore it's a linear transformation. It takes this whole space of vectors, which is the 3-dimensional space, and does some stretching, etc., that kind of stuff. And how you do it is just, again, like dot products. Dot products are ones where you have, I'll say A, B, C dotted with D, E, F, and these are these are all they're vectors, but I wrote them horizontally, sort of by accident. The point is that you just take the dot product of these two is just AD plus BE plus CF, right? This is a dot product of two vectors, ABC and DEF. Maybe I should put commas. Okay, so this is the dot product, and how you multiply matrices by vectors is just take the dot product of each row of the first thing with each column of the second thing, and its position in the output is just whatever row and column it was in. So this 201 times 201 was in the first row of the matrix and the first column of the vector, the only column. So therefore it becomes the first row in the only column. This 042 times this 201 is the second row and the first column. So therefore a second row, first column here, and etc. Right? So yeah, I'll talk a little more. I think this is something I should talk about next week, dot products and cross. Actually, well, I'll talk a little bit about cross products next week. There's another kind of product between vectors called a cross product that is not the same as this. It's actually much more complicated. It gives you a vector. I'll think about how much we need. I mean, we definitely should talk about this in terms of the directions. You absolutely do need to know that. The right-hand rule. If you don't know what any of these mean, that's totally fine. I'm going to talk about them. This stands for right-hand rule. Actually, I don't want to even write them. I'm not going to get it wrong. But anyway, but we'll talk about whether we actually need to go through how to do a cross product. But it's some other operation you can do to vectors to get them together into a new vector. In some sense, I'll just give you some geometric intuition. In some sense, this dot product tells you how similar two vectors are. So if you have two vectors that are very similar to each other, like they're almost in the same direction, the dot product will be very high. And if you have two vectors that are like perpendicular, their dot product is actually 0. So we can actually write this as, let's call this vector A and this vector B, right? This is the component expansion, but we can also write this as, I'll put it in red. A dot B is also equal to the magnitude of A, which is the length of the vector, whoops. The magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between the vectors. So if the vectors are at 90 degrees, pi over 2 apart from each other, so if you have one here and one here, right, the x-axis and the y-axis, for example, you'll have cosine of 90, which is 0. And so therefore their dot products of anything that's perpendicular, no matter how long they are, is 0, right? And dot products of things that are in the same direction, well, if they're exactly the same direction, if they're literally parallel, you'll have theta equals 0, therefore cosine of theta is 1, and therefore you just get the product of their magnitudes. But this is how you actually do it in components. Okay, so moving on. I'll come back to this next week when we talk about other like cross products and stuff. Okay, so now we're going to do some imaginary. Oh God. Yeah. Okay. The rest of it's all just imaginary number stuff. It's good to go over. Yeah. Okay. It's good to go over, I guess. Yeah. Basically whatever we're going to about to do in the quiz is kind of all you need to know about imaginary. I mean, I'll think about it and I'll come up with maybe more things, but this is like a little overkill. We don't use them very much in this class. It's not like I mean, we use them a little bit for waves, only in the sense that that of Euler's identity, which is the fact that this differential equation solves, or sorry, this e to the ix solves that differential equation, and you can write it as cosine and sine. Other than that, we really don't need anything else, but let's just go over it. And so we have e to the I cosine, or sorry, e to the I theta is just going to be cosine theta plus I sine theta. Yeah, this is Euler's identity. It just tells you essentially a geometric way to think about imaginary numbers, which is that e to the I theta on the complex plane, if this is the real axis, this is the imaginary axis. If you have a complex number here, we can write it, let's just forget about the length, let's just say the length is 1. If this angle between the vector that goes to the complex number and the real axis is theta, we can actually just write this number as e to the I theta. And the reason we know that is because, well, what's its length along the real axis? What's its real component? Usually we write it as a plus ib, right? That's usually how we write complex numbers. What's its real component? That's a. Well, that's, if this is just a triangle, this is just a right triangle, then the real part is going to be cosine of theta, right? Because if the assuming the hypotenuse is 1, cosine theta is adjacent, which is this part, over hypotenuse, which is, so this is just going to be cosine of that angle theta, whatever that angle is. And then plus I, now b is going to be the imaginary component, which is the vertical component. That's going to be sine of theta, right? Because it's opposite over hypotenuse. So that's going to be sine of theta. And so going from a polar coordinate system to a Cartesian coordinate system, Cartesian meaning x and y, in like the complex plane, is done just through Euler's identity, right? And of course, if this is not all complex numbers because there's no radius here, this is just if the radius, if the modulus of the complex number is 1. We can also, of course, write this as r e to the I theta equals r cosine theta plus I r sine theta. You can again see that if you just scale this hypotenuse to be r, you'll get this thing, right? And again, if they want, like, let's say they ask for the real component of this, we know it's just cosine of that angle, right? Yeah, now in the next question, they ask you specifically for the imaginary part of something. Now, of course, using this, we could just think, oh, it's just sine of the theta, but like, we don't really know what theta is. So it's actually probably easier to just do the algebra. So in this case, the algebra is just going to be 1, it's 1 over 2 plus 3i, right? Now, how do we, the i's in the denominator, we don't really know what to do with this thing here. It's sort of not clear what we do with it. And so what we have to do is multiply the top and bottom by something so that the denominator is always real, right? That's always what we want. We don't want i's in the denominator because they're very sort of hard to understand. If we multiply the top and bottom by, there's something we can multiply the top and bottom by so that the numerator and, the denominator is real. And what it is called the complex conjugate. Whoops, yeah, 2 minus 3i. It's just the same thing where you replace I with minus I. And the reason is because the first term is always going to be real, the first term in this expansion, because it's 2 times 2. The last term where you multiply the, like this thing and this thing, is also going to be real because it's I times I, which is a real number. But the cross terms are going to be the ones where you get extra i's. And so if you just switch the sign, so there's a minus sign here and a plus sign over here. If you just switch the sign, the cross terms are going to cancel out. That's basically the reason. But of course, we can't just multiply the denominator by something without multiplying the numerator. And so that's it. And then we need to, sorry, it's a little crowded over here, but the numerator is going to be 2 minus 3i. Oops, sorry. And the denominator is going to be, well, 2 times 2 is 4. We know the cross terms cancel because we get 2 times minus 3i and then 2 times plus 3i. And the other term is going to be, well, it's going to be minus 9 times I squared, which is minus 1, so it's going to be plus 9. So it's 2 minus 3i over 13. So the imaginary part, is minus 5 over 13, right? The imaginary part, by the way, when they say that, is the part, did I do that right? Oh, sorry, I don't know why it's 5. I don't know why I changed to 5. Sorry, I meant it's supposed to be 3. I just wrote it so poorly that I agree. Yeah, by the way, when they say the imaginary part, you don't put an I over here, just so you know. The imaginary part is a real number. Just that's, I mean, it's not like super critical. It's just like it's more of a technical, like a, what do you call it? The definition of imaginary and real parts is just always a real number. You just take away the I. It's just a thing proportional to I, so that you can write things like RE plus I times imaginary, right? That's how you sort of want to write it. Okay. The next one here is, it's asking you for, because it's put in bars, they're asking you for the, so I'm going to just do it down here. Because it's put in bars, they're asking you for, it's called the modulus, right? Or the length. If it was a vector, you'd call it the length. In complex space, you call it the modulus, but it's the same thing. It just means one way you could find it, well, actually the only way you could find it is by taking the thing squared and then taking the square root, right? Anything that you take squared and then you take square root, anything squared, by the way, is always a positive real number, right? Sorry, a real number. Well, okay. Sorry, let me rephrase this. Anything, oh yeah, sorry, that's what I was thinking. Okay, yeah. Any vector, if you have a single vector and you take the modulus, the length of that vector, you can square it and then take the square root. And the reason is you can do that is because when you square something, you always get a positive real number, right? And then you take the square root and you take the positive part of it, and it tells you the length. In this case, when we square a complex number, we actually can't just take that number and multiply it by itself. We have to multiply it by its complex conjugate, because, and the reason is sort of has to do with the fact that there's a certain, sort of metric on this complex space that's different than, it's not just a vector with like one entry and another. It's not just a two-dimensional vector. It has special properties to do with the fact that that there's an I here. So to square a complex number, you have to multiply by its complex conjugate. And so what we get is, well, this is going to be what? 3 times 3 is, yeah, one of the reasons is because we want this answer to be real always, and we want to cancel the cross terms. It's the same thing as before. So 3 times 3 is 9. And 4i times minus 4i is going to be 16 plus 16. And the I terms are going to cancel because they're cross terms and they cancel each other. Square root of 9 plus 16, you may have seen this before, square root of 25, and therefore the answer is 5. So this is 5. So in other words, the modulus of any complex number and the length of any vector is a positive real number always. It doesn't make sense to have a negative length. And similarly, it doesn't make sense to have a negative modulus of a complex number, but we have to use the special trick that to square a complex number always means to multiply by its complex conjugate. That's the sort of one exception we have to make to just using the complex plane as like a two-dimensional vectors. It's the one difference. Yeah. Right. Okay. So now we're gonna calculate square root of 2i. I'll probably have to do this. Actually, I'll do this over here. I know this is going to be like a really messy looking. There we go. So it asks for square root of 2i. Okay. So, well, we know because these are just products of things, right? Just because it's an I doesn't mean it's anything fancy. It's just a product. So we can write this as radical 2, which is a number, times radical I. But we can't just leave it like this, because square root of I is like, well, okay, what does that mean? Like, what? I don't, is that like, what kind of number is that? Is a real number? Is a complex number? Probably a complex number. But what we have to do is know that at the complex plane, we have the real part here, the imaginary part here. And we know that if 1 is here and minus 1 is here, we know that I is up here, right? And minus I, of course, is down here. Now, if we want to write this in polar coordinates, basically almost anytime you take any powers of complex number equals polar. I'm just going to write this. This is like a thing you should remember. Whenever you're like doing a complex number problem and sort of not quite sure how to handle it, basically if you go to polar coordinates, it'll be easier 90% of the time. And so what we're going to do here is go to polar coordinates. We're going to write, well, radical 2 is just a real number, so we don't care about that. But the I, square root of I, we're going to write in polar coordinates. What's I in polar coordinates? Well, it's going to be e to the, whatever this angle theta is, e to the I, whatever that theta is, which is going to be, of course, just pi over 2. So this is I, right? This is just a fact. I equals e to the I pi over 2. And let's just write the other ones now. -1 is e to the I pi, right? This is a famous equation because you can put the 1 on the other side and set it equal to 0. And then -I is e to the, well, we can write it two ways. We can write -I pi over 2, right? Because the angle could be seen as downward. Or we can write it as e to the I 3 pi over 2, right? Of course, all these angles are like cyclic. So if you add 2 pi to any of these, you would get the same number. So if we actually, what we really should write is I equals e to the I pi over 2 plus 2 pi n, right? This is the technical way to write it. We actually, and the reason I'm not just bringing this up to be annoying, we actually we will use this for waves because the n actually is important. But this is 2 pi n. The reason is because any n value here, this is still equal to I because it just corresponds to going around the circle a bunch of times, right? Oh, there's an undo. Should have just been doing that. Yeah. Okay, but of course, now let's just n equals 0, so we'll just take the principal value, the sort of obvious value. And now we have, okay, let's go back to our problem. Square root of 2 times I to the 1/2. There. Oops. 2. E to the I pi over 2. But this is the square root, so it's really to the 1/2, and therefore we get square root of 2 times e to the I pi over 4. And that's it. Right? This is the square root of 2 is a real number that we're totally fine writing this as r e to the I theta, right? This is how you write complex numbers in polar. So the r is just square root of 2. Theta is just pi over 4, and that's it. This is it. Now, if we want, we could go back and write this in, we could go back and write this as a plus ib, right, which is Cartesian. So this is polar, and this is Cartesian, named after Descartes. And yeah, again, like I said, polar is, like I said above, yeah, polar is very good at solving a lot of these problems where we're having to take powers of things, because any power can just be written as this thing raised to some fraction, right, or some number. And of course, raising something that's already a power to another power is just multiplying the powers. It's actually really easy in this case, as we just saw. But if we want to put it back to, like, let's say they asked you the imaginary part. Well, it's not obvious from the polar form what the imaginary part is. We have to actually put it in Cartesian, because then B is just going to be the imaginary part. Well, how do we do that? Well, we just use, as we said, Euler's formula again, and we say, well, we know that in this case, R. And we just say, okay, well, R cosine theta is what? Well, it's going to be square root of 2. Cosine theta is, well, what's cosine of, well, theta is going to be pi over 4, right? So theta equals pi over 4, R equals square root of 2. That's a 4. So therefore we get square root of 2 cosine of pi over 4 is, well, that's 45 degrees. So it's radical 2 over 2, right? And that's of course, we know that's the one value that's sine, cosine agree, right? Because it's like halfway or whatever. So we get radical 2 over 2. Now, what's radical 2 times radical 2 over 2? In the numerator, we get radical 2 squared, which is 2. Denominator is 2. So actually, this is just 1. 1, 1. And we get 1 plus I. That's it. That's the whole thing. If they ask you what the imaginary part of this is, so if they said, what's the imaginary part of radical 2 e to the I pi over 4? This is equal to 1. And what's the real part? of radical 2 e to the I pi over 4 is also equal to 1. Right? So here's 3 different ways of writing this complex number, which is, how do we even start with this? They just asked us what the square root of something was, right? Square root of 2i. Yeah, so that's kind of interesting. Yeah. Yeah, that's pretty much it. Okay. Oh, I can, is that easier if I zoom out or not? Actually, it is. It's harder for me to write small, but yeah, okay. All right, now let's go find the product. So I'll zoom back in right now. Again, I'll post this as like a PDF or whatever.
So since it asked us to calculate the number, we're fine leaving it in the 1 plus I form?
Yes, this is the actual simplest form you could leave it. I mean, I would argue that even the radical 2 e to the I whatever is also equally simple.
Right.
You don't need to actually write the separate components. I think this or the polar form is totally the simplest way you could write it.
Okay.
All right. So, any other questions about complex numbers so far? We have a few more complex number problems. Oh yeah, here's some more converting to polar forms. All right, so the product here we're going to do, we just did some problems where we already used this. Multiply the, just do like FOIL or whatever, right? And this time it's not gonna, the cross numbers are not going to cancel, of course, because this is not a complex conjugate of itself. So we get 3 times 5 is 15, minus 20i plus 18i, right? And now we have 24 times minus I times I, which is plus, oh, sorry, it's minus 24, right? Sorry, it's plus 24 because minus I times I is 1. So it's plus 24, and then we get 15 plus 24, whatever that is, then you add these here, whatever that is, right? That's it. Okay, I'm not gonna, I think we all know how to do it. I don't want to mess up some simple algebra in front of everyone. So, okay, now let's convert this to polar form. Right, so now we have it, it's sort of the opposite of what we just had. We have it in the form of cosine plus I sine, but we want it in the form of some angle. Now, it's not going to be easy to just say, well, 4 is just cosine theta and 3 is just sine theta. Like that's not easy, because that's like, well, what's theta? I don't know, like that's actually nothing, because sine of, or cosine of theta is never 4. So, it's going to be really hard to do it this way. What we can do though is say, treat this just like a geometry problem. This is identical to the geometry problem of saying that the x component of a triangle is 4, and the, oops, I forgot the sign, so let me undo this a little bit. The x component of a triangle is 4, plus 4, and the y component is minus 3, right? The only difference between, and then what they're asking for is the radius r, because we want it like this, the radius r, and this angle theta, right? Really, this angle is like minus theta or whatever, but yeah. So it's the equivalent problem. It's not, we don't have any like special things we have to consider, like the complex conjugate thing where we had to like think that there's a difference between complex numbers and vectors. This is identical. All we do is just say, we say this is called real and this is called imaginary. Otherwise, it's just like an x and y problem. And how do we do this? Well, r is just the hypotenuse of a triangle with lengths 4 and 3. We could do Pythagorean theorem to get the radius, which is going to be 5. So this is going to be 5 e to the I. Now all we need is theta, right? Well, theta is a little bit trickier, but using some trig rules, we can figure it out. We can use, well, because we know r is 5, we could do sine of theta is minus 3 over 5, right? Or let's just take absolute values. Let's say 3 over 5, and then we could add the sine ourselves. We could do that. We could do cosine, but let's just do it without knowing r, because what if they didn't want to know r? We wouldn't have to find it just to do this problem. Let's do it with just the 2 edges that they gave us. the only one that uses the opposite and adjacent is tan. So right, so we have to do tan theta is minus 3 over 4. Right now, actually, I'm just going to put absolute values because I'm just going to manually put the minus sign on the theta because I know theta goes down, so it must be a minus sign. So we can just pretend, like, in other words, if you flip this triangle over the real axis and you put it like up here, it would be the same problem, but we wouldn't have to worry about this minus sign. So the minus sign won't mess anything up. You can totally do it. I don't like minus signs. I like to like put them in by hand later. But that I'm not saying that's a good idea. I'm just saying that's what I do. So we of course know that this is going to be arctan of 3/4. Now, if you know what arctan of 3/4 is, then that's fantastic. I have absolutely no idea, but it's some number. Let's say it's, I don't know. You should actually put it in radians. I think actually I have it somewhere. It's like 6.9. I don't think that's right. Anyway, whatever. It's some number of radians. Anyway, this is the angle theta.
36.86.
36.
Yeah, 0.86 arctan of.
Oh, that's degrees, though, right?
Yeah, degrees. Sorry.
Yeah. No, that's fine. That's fine. Yeah, so you can put it in degrees if you want. Usually, when you write it like this, we would leave it in radians because of. It's kind of a silly reason. It's because so I'll just write the answer now. Yeah. The reason is because degrees are sort of not like people think of them as units, and you're not really supposed to have anything with the units in an exponential, whereas radians are sort of not units because they're like arc length divided by radius, so they're sort of unitless. Anyway, it's a little bit of a silly reason. I think of things in terms of degrees usually in real life, so you can leave it like that, it's fine. Of course, as we said, sorry, I forgot about the minus sign. It's minus because this goes down 36 degrees. We could also write it as minus 36 degrees is the same, the equals sign, triple equals means the equivalent to 360 degrees minus 36 degrees, right? 36 degrees, which is whatever it is, it's like 200 whatever, right? Or 190, 4 or something, right? So this, you could also write it like this because that would just be this angle here, right? And depending on your convention, you can totally write that. I like minus degrees because I think it makes more sense. And therefore, then all of your degrees will be less than 90 or less than 180. So it's sort of a little easier. But it's up to you. Okay, this last question is just combining things we've already done, which is 2 minus 3i is just a regular complex number. And now the second part, we're going to have to do that trick where we multiply the top and bottom by, this is 1. Multiply the top and bottom by the complex conjugate. And we get, 2 minus 3i plus 1 minus I over, and now the first term is going to be 1, the second term is going to be 1 as well, so it's going to be 2. Therefore, we can write this as 2 minus 3i plus 1/2 minus I over 2, and then we can just add the imaginary parts. We get a fraction, 9 halves or whatever, and sorry, not 9 halves, 7 halves or something. And then 2 plus half is 5 halves or something, so therefore we get some fractions. If they ask us the real part, imaginary part, we could just figure that out. Okay, so does anyone have any questions about, well, let me just ask, does anyone have a question about complex numbers? All right, does anyone have questions about any of these problems that maybe I did too fast or something? It would not be the first time someone accused me of that. Am I still recording? I am. Good.
I mean, I guess
Yeah.
like it'll be interesting to see all of these in concepts like in physics, like as you mentioned. So it'll probably make more sense.
Yes. So okay. So great. What I'm going to do, I think, is for next week, because we got through this, and it's actually a little early. I'll wrap this up in a minute. And unless anyone has any questions, I can totally answer them, but I'll wrap this up in a minute. And for next week, what I'll do is plan some problems that I think didn't make, so I didn't make this, obviously, the professor made it. So I'll add some problems that like, I think should have been on here maybe to prepare you for things, or like things from, because last year was the first year I did this. So I'll just talk about things that people really had trouble with, especially from the fall semester. And I'll put them in more physics-y contexts. Of course, you're not expected to know a lot of physics things already, but I'll just put them in a little more context, like maybe talk about acceleration instead of second derivatives and that kind of stuff, so that you're a little more prepared for physics problems, as opposed to, these are all pure math problems. These are not sort of physics-y type problems. They're completely math problems. So I do want to make sure you know, like, when to use a Taylor expansion, except besides when they just literally ask for a Taylor expansion. That's sort of not a good way to ask about it. So yeah, so I'll come up with those. If anyone, as I said, if anyone has like a thing that they're like, I think this will come up in physics and I, in this class, and, or I just want to know about this and I'm very, I feel like I need a review of this, feel free to email me and I'll sort of incorporate it for next week. Let's see. I think that's about it. Yeah.
Yeah, and Stoner, this is for the scientific foundations of engineering.
Yes, yeah. That's correct.
Okay, you kept referring to physics, so I take it that.
Oh, sorry. Yeah.
I take it the class is going to be focused a lot on real world physics.
Yes, so it's sort of so it's definitely an engineering focused class, obviously. I keep calling it physics because that's what my field is. I'm a grad student in physics, but and yes, the class and the book and all that stuff is called Principles of Engineering, and it's basically like a tour of physics concepts, but applied to a lot of sort of examples in a very engineering type way. So don't worry that it's not going to be like pure theory all the time, where you just have to like imagine situations perfectly all the time. It's not that kind of physics. It's like a very engineering focus. Like here's a situation, find the force on this thing, or find the lowest amount of force you need to do this thing, right? So I call it physics just because I'm sort of used to teaching classes called physics. But yeah, this is the scientific foundations. It's a little fat. I would say if there's one thing that's not perfect about it, it would be that each concept doesn't go in depth a lot, which may, it depends. Maybe you don't think that's a bad thing, but it's sort of like we go through each concept relatively quickly and don't go super, super detailed on it in a way that I think really prepares engineers probably very well for, seeing unexpected concepts that they need to learn about, or figuring out what they need to learn for their specific thing, but it doesn't like bog you down with doing the same types of problems just harder and harder for like a month or something like that. We're not going to do that. We're going to do very like move on quickly, but sort of get really the principles of each topic. And especially in the spring when we talk about electricity and magnetism and waves and optics and stuff, he really wants to get the principles of it without having to just slog through like 100 problems on it. Which I guess now that I'm saying it is probably a good thing. So I didn't mean to suggest it was a bad thing, but yeah, it's not going to be like, if you've taken physics before, it'll probably be a lot different than that.
Okay. Yeah. No, okay. I understand. It should be good.
Yeah. Hopefully the professor will email, if he hasn't emailed you already, he'll email you soon with sort of the introduction or how he's going to teach. I'm not quite sure what he's going to do for the online stuff yet. I'll probably have my office hours online for a while because the suite where this class is usually like meets is closed for, I don't know how long they're going to be closed, but definitely for like the next few weeks. So I'll have my office hours online. Office hours are going to be basically like this, I think, where I just write on a blank sheet of paper and you're free to ask me questions. And I think they're going to be 2 hours twice a week, twice, maybe 3 times a week. So there's plenty of them because the class only meets once a week. So there's sort of a lot of extra time for office hours. And yeah, we'll see how it goes. Obviously, if people want me to do one thing or another thing, we'll work on getting it in a place where everyone feels really like they're getting the most out of the office hours. And I'll also, last year, what I started doing very quickly is recording the office hours and putting them on YouTube. And so I'll put this video of this, what I'm talking right now, I'll put this on YouTube, and I'll also put the office hours for this semester on YouTube. So if you don't want to come virtually, you can just watch them later, right? Or before the test, you could watch a few of them if you want. People like doing that last semester, so yeah. All right, well, I'll ask one more time if there's any questions about anything, and if not, I'll wrap up a little early today, and then I'll start figuring out what we're going to do next week.
I had a question real quick.
Yeah, sure.
I know you said the class is going to touch on like a variety of concepts pretty briefly. Is it going to touch at all on like fluids or thermodynamics? Some of the math. Okay, excellent.
Yes, we will.
Excellent.
We will talk. There's a unit in the, I believe those are both in this. I believe those are both in the spring. Yeah, there's a unit on fluids and Bernoulli's principle or something. Again, it's not super. It's not like like huge differential equations about it, but you'll have to like vaguely find use the density of a fluid in some equation or something for the whatever. And for the other one, thermodynamics. Yeah. Yes, we will. There's actually kind of a lot on thermodynamics because I think of just the use that I think a lot of people have had in the past, in last year, with a lot of people work in industries where they need to talk about thermodynamics. And so we'll have a unit on entropy and heat engines and all that kind of stuff that perhaps you've learned about before and hated, and I don't blame you. But no, it'll be done really well. Yeah.
This might be a very open-ended and poorly worded question.
That's right.
But, so differential equations, I just recall it being like not one of my favorite courses.
Yeah.
Even though I generally like math heavy stuff. I guess, and the reason for that being is like I can like the question we had here that was involved I can grasp the concept of like it being the derivative. I guess I just don't, and again, it may be too open-ended, but like, what is like the purpose of calling it a differential equation, or how is it different than just saying like, this is the derivative?
Well, so it's actually not. Like, I think the fact that there's a whole class on it and it's called like something else is a little intimidating, like compared to what it actually is. You're right. It's literally just saying that the derivative is related to the function itself in some way. In the case of this problem, it's saying that the second derivative is literally just minus of the function itself. And the physics application, I'll just tell you real quick. Well, it is actually one of the first units, so that we'll learn in like probably a couple weeks. For springs, so if you have a block with a mass m, and this is a spring, the force due to the spring this is called Hooke's law, is minus kx. K is some constant called the spring constant. X is literally the position that the mass is in. Now the minus sign here means that if you push it in the positive x direction, let me undo some of these lines. If you push it in the positive direction, which means to the right, the force is going to be to the left, right? Whoops. And that makes sense because the spring is going to pull it back. Also, if you push it in the negative x direction, which means to the left, the force is going to be to the right. It's going to be the opposite direction. So that's sort of the essence of a stable state. And if we, instead of writing F, if we write ma, F equals ma, right, from Newton's law, which is also equal to m times d squared x dt squared, where, of course, acceleration is just the second derivative of position. Again, we'll talk about this if you haven't seen these types of things before. We'll talk about this. And if x is a function of time, this, if we just divide by m, and there's just a constant here, that's basically this differential equation that was given in the, whoops, there we go. That's basically this differential equation that was given in the homework. So this is literally a relation between the second derivative of the position and the position itself. And it's all to do with the fact that springs pull you back to sort of in the direction opposite you're going. And so that's an example. And then another example, I guess, for the opposite one would be like a ball on a hill, where if you go one way, it's going to want to, gravity's going to want to push you the same direction kind of thing. And it's a little less clear why that's, well, anyway, it's unstable. This one is stable because it wants to restore your force. So this is honestly, every time we do a different equation, if you just think it's kind of like a spring, I believe every single time you'll be right. Because it's just like, that's sort of the essence of it. I mean, maybe this is just me because I've done physics things more than math things, but I think of different equations, as like springs. Like basically like they're all about relations between objects that pull and push things, as opposed to like just a pure thing that's like functions are related to their derivatives. Like that's a little abstract and like what class of functions? Oh, it's just some cosine sign. I guess I have to know that. That's all true, but once you get used to it, I think you do see that this is going to be very different than a differential equation class, is my point. This is going to be much more physics focused and sort of intuition focused. Yeah, so someone asked, can be put like a derivative can be the infinitesimally small area under the curve and analyze the momentary change in the function. Yeah, I mean, you could totally talk about derivatives and integrals in that sort of geometric pattern type way. That's actually, yeah, I mean, that's definitely something. So if this is a function, you could talk about well, that's not a good function. So it goes like that. You could talk about the derivative at this point as the slope of the line right here. And really how you could measure that is by measuring the function at very close points and taking the line that passes between them. And as you go closer and closer together, it actually approaches like tangent to the line, like the actual slope. And then the other way to do, to talk about integrals, is that you're just sort of breaking up the area under the curve into rectangles and adding up the areas of all the rectangles and finding that. That's a totally valid way to do it. You're free to do it that way. I think you'll see that thinking of it's not always easier to think of the actual pictures of the graphs of the function. Sometimes it's actually easier when you learn the physics thing to actually think of the physical situation that's happening. I actually think this is like a better way to learn calculus. Physics is a better way to learn calculus than calculus class, in my opinion. Don't like quote me on that or anything, but like I think that's sort of true in the sense that like derivatives are just some abstract thing that has to do with slopes and tangents and lines that touch curves and stuff. And when you do talk about physics, you learn, oh no, the velocity is the derivative of the position over time, right? Like you have a position that changes over time, and at every instant there's like a change in that position. That's called the velocity. And once you start to think about that in acceleration, once you start to think about those things in the physical sense, you really interpret the derivatives, at least derivatives in time, and integrals in time too, as physical things, which we'll talk about in the future too. So, yeah, so that's definitely true that you can think of things like that. And I think again, like I said, all the differential equations and all the calculus, I think in the class are much easier to understand than they are on this quiz and in a calculus class. So if you're really worried about calculus, but you sort of know all these rules, I think you'll be okay. If you don't really know the rules, like you don't know how to integrate things and stuff, I would just make sure you review that on those websites.
Kind of piggybacking off of that, do you think it'd be worth going over like how to solve a simple homogeneous differential equation next time, or do you think that won't be necessarily the content?
I could do that. We definitely will need to do that like once. Like I said, there's like a few differential equations you need to solve, and you'll sort of end up having to memorize the answers basically. I mean, they're not sort of complicated things to memorize, but there's sort of almost no way to, you're sort of guess and check. That's how it works. Yeah, and the main ones are going to be the ones I've just showed. But like, for example, this one, there's also ones where you add a term like b, whoops, what am I doing? Yeah, you add a term like b dx dt, where this is a first derivative. So this is not, this is second derivative, this is zero derivative, this is a first derivative. This ends up being like what's called a drag force, which is because it's proportional to the velocity. Now this has a fundamentally different solution than, it's not just cosine sine, it's cosine sine plus what's called a damping term. That's a good idea. I'll talk about that next time. I think I'll bring up another differential equation. But again, I don't want this to be like, they're not sort of brand new. There's sort of a finite list of differential equations that you'll have to sort of know about. And they're basically just springs and springs with drag. That's kind of the whole thing. Yeah, that's a good idea. I'll write that down. Yeah, and they'll all be homogeneous. By the way, if you know about differential equations, we'll never do any inhomogeneous differential equations in the class. Meaning that we'll never have one where like one of these has an x in them, or sorry, one of these has a t in them.
Right.
So like if you could totally have, there's books and, sections of libraries probably on how to solve crazy differential equations. But we're going to do sort of ordinary first 0, 1, and 2 derivative homogeneous differential equations. We're not going to do any with constant coefficients. We're not going to do anything with like functional coefficients, stuff like that. And we will do a driving force, one example of a driving force, but that'll be like a very simple, like, I can talk about that next time, actually. That's yeah, driving force and damped. Yeah, and there, again, like I said, there's sort of just the solution, and you sort of are supposed to, you're supposed to kind of understand what each term in the solution does, but not necessarily like how to derive it from scratch with just like a stick or something. Like,
yeah.
anything
Another
else?
question
Yeah.
I had was, so it asked us about our proficiency with MATLAB, and do you know like how much we're gonna be using MATLAB, what we should focus on reviewing?
Yes, so you'll have to do MATLAB for one project in the fall and one project in the spring at the end. Actually, I think in the spring it's optional. So in the fall you'll have to do one project, and what it will be, I can't tell you the specifics. Actually, I don't even remember the specifics, but it's something to do with like a projectile, and all it is going to be like plot the path of a projectile where you have to like iterate over each step. So like each little branch of the function is like in other words, you have like a parabola, like a projectile that goes like a baseball that has an initial velocity and it's under gravity, and you just have to basically compute each step like this and basically find out its path using small steps. And each time step, you're going to have to compute, okay, what's the new velocity based on the gravitational acceleration, et cetera. We're going to learn all about this, so you don't need to like conceptually figure any of that out. But on MATLAB, you're going to do things like iterating loops and stuff, and then plotting things. It's not going to be like some crazy matrix, it's not going to be some crazy matrix solving different, you're just going to do some relatively simple step iterating. And then there's one part where you use, it's called ODE 45. It's like some, I think it's called 45. It's some differential equation solver. But again, when I say that, I just mean you literally. It does it for you. It does it for you, exactly. You don't need to like, again, I don't even know what you're not gonna do something crazy with MATLAB. It's something very constrained, and the project has a lot more steps other than the MATLAB steps, so it's not all about that. And you can work together on that project too. That's like a group type thing. Yeah, and so I think if you're very shaky, if you've never seen it before, I would definitely watch some videos. First of all, get it installed. Watch some videos. Hopefully they sent you some MIT videos. I told them about those.
Yeah, they did, yeah.
Okay, good. So that's a very short course. It's very old. I understand it looks like it's very old, but all the main features should be the same. Also, you could you go on YouTube and watch some tutorials. They're probably actually better anyway. I just assumed that the MIT one that I watched was going to be the best one. But yeah, you could just look up some like how to do projectile problems on MATLAB. I mean, don't tell anyone I told you to do this, but if you just look up that, you'll probably find like very similar types of things that we'll need to do. And yeah, if you just look again, sorry, I was saying if you've never seen it before, if you've never seen MATLAB before, get it installed and go and just find how to do some very simple like multiplication of two things, and then maybe multiplication of a vector and a vector, or just something very simple, and how to define variables. Look up those things. I'm sure you could find those on any tutorial video. And if you know how to do those things, and you know how to like vaguely do sort of loops, you should be totally fine. You might want to just read more things, but again, if you only know that and you start the project, you'll have plenty of time to figure out all the details anyway.
Okay.
I have Keegan, you may know this, you may not know it. I went through the handbook there and installed MATLAB. The license number didn't work, although I was still able to do a personal license with the Northeastern EDU email, and it installed, but the license and key didn't seem to work. You know, follow the instructions, go to license manager, plug it in.
The one in the PDF that they sent?
Yeah.
I see. Yeah, I don't know why they send, I've always thought that you had to do it through NEU.
No, we did. I went through NEU and it went through the email address for NEU, and everything worked perfectly, except when it got to the license. I mean, it's installed on my machine. It actually just gave me a licenence. So.
Okay, yeah, I would say, if you're having trouble with that, for everyone else, go ahead.
I didn't have a problem. What the only is more the instructions of using that license, right? Key, the license and the key.
Right. Okay, that's good. I'm gonna write that down.
Yeah. And so the real question is maybe that's an old license, or maybe I'm supposed to use it. I guess my question is do we have to use that license? It did install, and I have the Windows on my PC.
So I didn't notice that in the manual. Last year, what I recall is that I was just telling everyone to use their NEU email, and it should automatically download. Yeah, so I would just disregard that might be an old license, and because they've just switched as of literally like a month ago, they switched everyone to like Microsoft emails, and they renewed a bunch of software stuff. So I think that is probably an old license that it doesn't work anymore. So yeah, just make sure if you have trouble downloading it, even if in your NEU, anyone else, just like send me or anyone from the Gordon group an email, and they'll direct you to whoever knows how to do that.
The directions worked perfectly other than that, and it did install and load, and so the rest of it worked fine. It's just the license number itself.
Great. Okay, yeah, that's good to know. I'll let someone know about that. Okay, anything else with anything? All right. I will post this video on my YouTube channel, and if you look at the previous videos on my YouTube channel, you'll see all the office hours from last year. So feel free to watch them if you want. They're about things we haven't talked about yet. But in the future, I'll do my office hours, but you can also just watch those if you prefer. Maybe you prefer me last year than me today. I don't know. So you're free to look at those. And actually, I just remembered. I can't believe that. There's also a MATLAB review from last year on my YouTube channel. I just remembered. It's not by me. It's by the guy who did it before. And he's better at it than me. So you can actually watch those. I'll send those in a link when I send this link to this video too. So that'll be really good. Okay, I will.